Hello everybody, my name is Mehdi Bagherzadeh. I am an assistant professor at Oakland University. Today I'm going to present our study of the characteristics of real-world actor bugs. Nowadays, concurrency is everywhere, from hospitals to stock exchanges to power grids. There are two major programming models behind this concurrency: multi-threaded concurrency and message passing concurrency. Despite the dominance of multi-threaded concurrency, message passing and its realization in actors is becoming increasingly popular. For example, PayPal uses actors to serve more than 1 billion transactions a day. Unlike multi-threaded concurrency, in which threads communicate using shared memory and locks, actors communicate using asynchronous messages. This makes actors less prone to some of the standard multi-threaded bugs, such as low-level data races and deadlocks. However, actors come with their own bugs that are not only different, but also largely unknown. To understand the real-world actor bugs and their characteristics, we formulate 4 research questions. 1. What are the symptoms of actor bugs? 2. What are the root causes of these bugs? 3. What APIs do these bugs use? 4. How different these bugs are when they come from different sources. To collect the set of our actor bugs, we perform the following steps. We construct a set of real-world bugs from both Stack Overflow and GitHub. Stack Overflow is the most common question and answer website with more than 18 million questions and 4 million developers. Stack Overflow gives us insight about the bugs for which developers ask questions about and receive help in fixing. Similarly, GitHub is the most common code repository for open source software with more than 100 million projects and 24 million developers. GitHub gives us insights about the bugs that developers leave in their code but find and fix later. There are several industrial-strength actor frameworks and languages. Among these, we focus on Akka because it is growing faster than others. For example, the number of Akka questions in Stack Overflow is 48 times the number of questions related to Microsoft or Linux. To collect Akka bugs in Stack Overflow, we identify Akka questions that include code and manually analyze these questions to see if they discuss bugs and their fixes. In total, we analyzed near 4,000 questions, answers, and comments and find 130 bugs and their fixes. Multiple authors participate in this analysis and iterate and refine until they all agree on the set of bugs. To collect Akka bugs in GitHub, we identify mature Akka projects and their commits and manually analyze these commits to see if they discuss bugs and their fixes. In total, we analyzed more than 3,000 commits, messages, original and modified code snippets, issues, and pull requests, and find 56 bugs and their fixes. Again, multiple authors participate in this analysis and iterate and refine until they all agree. Our final dataset includes 186 actor bugs. The size of our dataset is in line with the previous work. For example, Heden and Zhao study 126 actor bugs. Because of their complementary characteristics, we include both runtime and compile time bugs in our dataset. 89% of our bugs are runtime bugs, whereas 11% are compile time bugs. To understand the characteristics of our bugs, we follow these next steps. For our Stack Overflow bugs, we manually analyze the text and code snippets in their questions, all the answers and comments to understand the symptoms, root causes, API usages, and the differences of these bugs. Similarly, for our GitHub bugs, we manually analyze the messages and code snippets in their commits, issues, and pull requests. Similar to data collection, multiple authors participate in these analyses and iterate and refine until they all agree. Now we can answer our research questions. Research question 1. What are the symptoms of actor bugs? We find that the symptoms of actor bugs can be classified into 5 categories: error, unexpected behavior, incorrect messaging, incorrect termination, and incorrect exceptions. Among these, error is the most common with more than a third of the symptoms, and incorrect exceptions is the least common with only 2%. A symptom denotes the impacts of a bug when it occurs. For example, the impact of an incorrect exceptions bug is that an intended actor does not throw, catch, or handle an expected exception. To better understand our symptoms, we present examples of bugs with these symptoms. To illustrate, this code, which is written in a Scala Akka, shows a buggy actor program with an incorrect exceptions symptom. The code declares the application app and the actor my actor with a constructor this. In app, the developer intends to create the actor act of type my actor as a child of app and catch the exception that its creation throws. The invocation of actor of on context creates act as a child of app. However, this program is buggy with the impact that app cannot catch the exception that act throws. This is because in Akka, an exception that is thrown by an actor can be caught and handled only by its parent, which is an actor itself. Here, app is an application and not an actor, and thus cannot be the parent of act and cannot catch its exception. We show the relation of our symptoms with the findings of the previous work. An example relation is that 3 of our symptoms overlap with all of Bianchi et al.'s symptoms. Bianchi et al. Surveyed the existing actor testing tools and classified 3 symptoms that these tools use to identify buggy executions. In contrast, 2 of our symptoms, which are incorrect messaging and incorrect exceptions, are new and cannot be found in the previous work. These 2 new symptoms account for more than 1/4 of our bugs. Finally, we discuss the implications of our symptoms. An example implication is that the current actor bug finding tools use crash, deadlock, and assertion violation as symptoms to identify buggy executions and find bugs. Our symptoms overlap with the symptoms that these tools use. However, we also find symptoms that are new and cannot be found in the previous work. Current and future tools can use our new symptoms to extend the set of buggy executions that they consider and find more bugs. Research question 2. What are the root causes of actor bugs? We find that the root causes of our actor bugs can be classified into 10 categories, ranging from logic to messaging patterns to untyped communications. Among these, logic is the most common root cause, with about 1/5 of the root causes, and untyped communication is the least common with only 1%. A root cause specifies the main reason for the occurrence of a bug. For example, the reason for an explicit lifecycle management bug is that Akka requires the life cycles of actors to be managed explicitly by developers. This means any mismanagements of actor life cycles can cause bugs. To illustrate, this code shows a buggy actor program with an explicit lifecycle management root cause. The code declares the actor parent and the actor child. In parent, the developer intends to send the message do cleanup to the child C, wait for its cleanup, and then stop and terminate C and itself. In Akka, the operator question mark sends a message with a future result that can be waited on. Post stop is invoked by Akka when an actor terminates. However, this program is buggy with the impact that C does not perform any cleanup. The root cause of this bug is that during the life cycle of actors in Akka, a parent terminates only after all its children terminate, and not before. Therefore, when post-stop of parent is invoked, C is already stopped and cannot receive and process the cleanup message. An example relation for our root causes is that 6 of our root causes overlap with Hedden and Zhao's root causes. Hedden and Zhao study 126 Akka actor bugs and classify their root causes. In contrast, 4 of our root causes, which are API confusion, model confusion, misnaming, and misconfiguration, are new and cannot be found in the previous work. These 4 new root causes account for about 1/3 of our bugs. An example implication for our root causes is that current actor bug testing tools use patterns of root causes to find bugs that match these patterns. Our root causes overlap with the root causes that these tools use. However, we also find root causes that are new and cannot be found in the previous work. Current and future tools can use our new root causes to extend the set of patterns that they consider and find more bugs. Research question 3. What APIs do actor bugs use? We find that our actor bugs mostly use 8 Akka API packages, ranging from the package actor to serialization to routing. Among these, the package actor is the most common with 81% usage, and routing is the least common with only 0.2%. We also find that 97% of API usages are for only 3% of Akka packages that are specific to untyped and local actors. An example implication for our API usages is that current bug-finding tools mine API usage patterns and find bugs that violate these patterns. One problem with these tools is that their mining processes do not scale to large code bases. However, we find that most API usages by actor bugs belong to a few packages for local and untyped actors. Current and future tools can use this to direct and therefore scale their mining processes to large code bases. Research question 4. How different are the characteristics of Stack Overflow and GitHub bugs? We find that symptoms, root causes, and API usages are significantly different among our Stack Overflow and GitHub bugs. For example, the incorrect messaging symptom is about 4 times more common for Stack Overflow bugs than GitHub bugs. An example implication for our differences is that existing bug finding tools use characteristics of the bugs to build models that can predict these bugs. However, similar models do not exist for actor bugs. Current and future tools can use our bug characteristics to build models that can accurately and separately predict both Stack Overflow and GitHub actor bugs. Two previous works are the most related to our work. First, Hedden and Zhao study 126 Akka actor bugs in 12 projects and classify their root causes. To compare, 4 of our root causes that account for about 1/3 of our bugs are new and cannot be found in this work. Second, Torres Lopez et al. Studied 23 actor bugs from 11 previous work and classified their root causes. To compare, 9 of our root causes that account for 85% of our bugs are new and cannot be found in this work. In addition, these works only study the root causes of actor bugs and not their other characteristics that we study. Using tags, keywords, maturity criteria, and manual analyses to identify bugs and their characteristics is a threat. To mitigate this threat, we closely follow the best practices of the previous work. Use of Stack Overflow and GitHub to find bugs is another threat. However, the large number of question and answers in Stack Overflow and projects in GitHub could help mitigate this threat. The complexity of concurrency bugs and its impact on their understanding, reporting, finding, and fixing is another threat. To mitigate this threat, we closely follow the best practices of the previous work and study only bugs that have been found and fixed. To summarize, in this work, 1. We construct a set of real-world actor bugs from Stack Overflow and GitHub. 2. Identify and classify their symptoms, root causes, API usages, and differences. 3. Present examples of bugs with these symptoms and root causes. 4. Study the relation of our findings with the findings of the previous work. And 6. Discuss the implication of our findings. All the data that we use in this study is publicly available at this URL. Thank you, everybody, and now I'm ready to answer your questions.